Good morning, everyone. There's this X right here, so I feel like I'm supposed to stand right here. Is that what this is for? No.
Sure.
All right, good morning, sentient beings. I say that now because I watched that I/O demo about duplex, and I'm really not sure anymore. So today I want to talk to you about security, in particular modern security in the cloud and with microservices and cloud environments. For those of you that might not recognize me, my name is Seth. I'm a developer advocate for Google. Google's a sponsor. I brought donuts, as mentioned. If you don't like Google, you like donuts, so please stop by the booth. Prior to Google, I worked at HashiCorp. Prior to HashiCorp, I worked at Chef. Prior to Chef, I worked at Custom Ink. You might recognize me from things like ChefSpec, Berkshelf, FoHi, Terraform, Vault, whatever. But today I want to talk about security. And it's important to note that when we think about traditional security, the way that organizations think about security is this black box. I'm going to put a lock around it, and it'll be great. And the moment that someone penetrates that outer lock, kind of all hell breaks loose. Right? We don't think beyond the surface area or the outermost perimeter. So what I'm going to do today is I'm going to challenge all of you to start rethinking the way that we think about security, less in terms of a prevention, but more in terms of a responsive behavior. So let's talk about traditional security. So this is a traditional architecture. For companies that have been around 10 or 15 years, this will look really familiar. You have some load balancer. It might be like a hardware-based load balancer, like an F5. And that's hitting a firewall. And that firewall terminates TLS at your edge. So whatever that is, probably a physical data center. And then that edge comes inside the secure area. Right? You've crossed the moat of the castle, and at that point, everything is trusted. And it's important to note that monoliths are very common in this architecture. So your application might talk to a database, but notice that there's no microservices in this architecture. So we have an application, it's talking to a backend database, and all of the interactions are secure, right? They're in the secure domain. But when we look at kind of a more modern architecture, it starts to look a little bit more complex. How many people have an architecture that looks something like this today? Right? So we have multiple services, multiple networks, multiple subnetworks. We have services talking to one another within that network, which is an unprivileged area. We have networks, services talking across different networks, possibly over the public internet. And we don't have a physical firewall anymore. Instead, we rely on things like firewall rules and routing tables to help do the security. And our load balancer might no longer be a physical load balancer like an FPGA. It's a software-based load balancer. Even more so, things get a little bit more complex when we start thinking about hosted services. So up there in the upper left-hand corner, you can see the managed services. Those are things like Google Cloud SQL or Amazon RDS, these databases as a service, right? Cloud Memory Store, Redis as a service, where no longer are you managing a server, but instead you're communicating with a third-party API, and you somehow have to manage the security of the data that is going into it and the data that is being transmitted to it via TLS or gRPC. So when we start thinking about architectures in this way, and it's important to note that the reason the industry is moving towards this architecture is that it allows better acceleration, it allows us to do better DevOps, it allows us to collaborate, et cetera, because each of those teams can own a service and they can iterate independently. But kind of the trade-off there is that we introduce significant complexity, right? I think everyone can agree that this was far simpler than this. But with complexity comes capability, right? And that's really the goal here, is to introduce capability. But we can't forget about security. So we have to stop thinking about security as this perimeter-based firewall, right? This is a row of lockers in a school. And the moment someone cuts one of those locks, everything inside the locker is accessible. All of the books, all of the lunch money, it's all available for anyone. If instead we had an outermost lock, but then we also wrapped all of our books and all of our lunch money in different locks with different combinations, that's a far more defense in-depth approach to security. So we have to start thinking about security like different layers of an onion, if you will, where it's not just like an attacker gets past the first layer and they have the keys to the kingdom, but instead we need to look at this moat castle thing that I found on the internet. So this castle thing is super fortified. There's a there's like a moat down there, and that wall is really steep, and then there's these like stairs that are designed to put the enemy in the disadvantage because you can just push them off, right? There's all of these techniques that actually date back, to medieval times that showcase how we can do defense in depth. And because of the way we architected applications in the past, we didn't think about defense in depth. We only thought about perimeter security. So what I'm challenging everyone to do is to start thinking like the past so that we can move towards the future. And cloud security actually helps. So one of my favorite quotes is like, if security is someone else's part-time job, are they as good as someone who's doing it full-time? So if you choose to use a cloud provider or multiple cloud providers, you're going to get some of the best and brightest and smartest people in the industry who are constantly thinking about attack vectors and security threats at layers that you don't even think of. So I'll give you some examples, like physical security. I'm going to talk about like Google data center specifically. Some of the things we've talked about publicly, like we design our own custom biometrics and access cards at GCP. And the reason for that is that if we use the third party, a government agency or a nefarious party could compromise that agency and have them manufacture vulnerable goods that could then lead to someone accessing our data center. Right? These are things that, as an application developer, I never think of. Right? But the folks who are thinking about security and these attack vectors are. It's the same reason we run all our own network cable. Right? We have our own backbone. We don't rely on the public internet. And that's because the nefarious actors could inject themselves in that party. The coolest thing on here is the laser intrusion detection system. It's exactly what you think. But a bunch of things. And again, a lot of these things are not unique to Google. There are a lot of data centers that have great physical security. But these are things that, as an application developer, like I'm a Ruby developer, a Python developer, a Go developer, like I generally don't think that the security vector is going to be someone connecting to like the undersea cable and intercepting my traffic. Right? But these are the things that these security teams who are dedicated think about constantly. Their tinfoil hats are much larger than our own. At GCP, we also have hardware security. So we have custom boot modules that verify the system integrity at boot time. So when the system boots, if anything has been modified, right, any packages have been changed or any hardware has been changed, we have custom boot modules that verify that. So it's really difficult for someone to run nefarious code or malicious code inside a data center. A lot of cloud providers also offer things like automated vulnerability scanning at the application layer, right? So there's some open source tools that do this. There's some proprietary tools that do this, and some cloud vendor tools that will do this. And they'll basically inspect your application and say, hey, these requests look invalid, or hey, this is a security vulnerability. You should take a look at it. Again, this is happening at the application layer. So what are the features of modern security? Well, I think the first one, and probably the most obvious one, is just encryption. Encryption everywhere. But it's encryption through unified APIs and codified best practices. And you'll see this phrase again in another slide. Right? So we need to encrypt everything. Right? We need to encrypt it in transit with TLS. But we also need to encrypt it at rest with things like AES or some type of modern encryption. We need dynamic, time-based, and revokable credentials. So today, a very common way in which, say, a front-end service gets permission to talk to a back-end database is someone Googles, how do I make a Postgres user? They go to Stack Overflow. They copy and paste the script. They generate a user. They put it in a text file. And then that gets checked into source control. And 6 months later, you're on the front page of Hacker News because you got pwned. And this happens repetitively over and over and over again. If you work for an enterprise, it's a little bit different. You have to file a JIRA ticket, and then you get the database credential emailed to you. The challenge is that all of the front-end servers are sharing this credential. It's difficult to rotate them. If that credential is compromised, we take the entire application down because every front-end server is sharing it. Additionally, we have to page people and get all these different people in the room to revoke those credentials, and they never expire by default. So they could live for years and years and years, which increases the surface area for them to be compromised. So instead, we have to start thinking about security as dynamic, time-based, and revocable. Right? So one of the key pillars of the DevOps movement was to treat servers like cattle, not pets. And what I advocate for is extending that to security. Right? Let's stop treating secrets like pets, where we hand them to config management piece by piece, and instead start treating them like cattle, where we just have hundreds of thousands of secrets, And we use other tooling to create them, revoke them, and time-base their access. And again, I'll say it again because it's incredibly important, is that we need a unified API and codified best practices for doing this. If we want application developers to take security seriously, we cannot require that they have a PhD in cryptography in order to be secure, right? We should not put the onus on a Python developer or a Ruby developer or a Go developer or a JavaScript developer to say, did you pick the right cipher suite for encryption? Right? Instead, our security team should be making those decisions and choosing those best practices. And instead, we say, hey, here's an API endpoint. If you give data to that API endpoint, we will make sure it is stored securely. And we will handle the encryption, and we will handle the algorithm choice, because that's our domain expertise. If you want to be secure, here's the API and the interface that you should adopt to be secure. And one of the ways you can do that is through the open source tool Vault. So one of my missions is to make Vault on GCP amazing. So I've been doing a lot of work to make Vault super cool. But instead of telling you that, I'm just going to show you that. And I put a slide that says live demo in, so I couldn't back out. So who's excited? Those were all the duplex bots that I paid to be here. All right. So what I have here is not anything you can see. That's cool, right? Let's fix that. Of course, this went over there. See, now you know it's live, because I already messed it up. All right, so what I have here is a terminal. Some of you are familiar with this. And I have a Vault server that's running on GKE. So GKE is the Google Kubernetes engine. It's kind of a managed Kubernetes, but you could run this on a VM if you really wanted to. So what I'll show you here is that we have this highly available. I'm telling you, live demos are like amazing, aren't they? Aha. OK, so what I have here is this Vault cluster. It's using self-signed TLS certs, but that's irrelevant. It's running in high availability mode. All of this is kind of magic. What I'm going to show you is kind of how Vault changes the way that you think about secrets management in a kind of a production environment. So in Vault, we have this notion of authentication, similar to like logging into a website. You put in a username and a password, and you authenticate to the system. So what I'm going to do here is I have this script that will create a few users. So I'm creating, I think, 4 or 5 users. So we have a user named Sally, Bobby, Chris, and Devin. These are going to be our 4 users in the system. You can authenticate to Vault via like LDAP and SAML and all of those other things. But for now, I'm just using like generic username and password. What will happen is that as a user, I will authenticate to Vault and get credentials. On the flip side, if I'm a machine, like a service or an application, I also authenticate to Vault directly. So no longer does a human sit in the middle of that process. So a human does not generate a credential and put it in a text file. Instead, the application or service at runtime goes and says, hey, I'm service ABCD. Here's my authentication. Vault verifies that. Then that service, as an entity in the system, requests a credential. So no human ever sees that credential. We'll see some examples of that in a second. So the easiest way to think about Vault is that it's this kind of pluggable system of a bunch of stuff. And one of the stuffs, or backends as they're called, is the generic key value store backend. So you can think of this like encrypted Redis or encrypted memcached. You're going to give Vault some data in plain text. Vault will encrypt it in transit with TLS. And then it will encrypt it and store it in the underlying storage backend. In this case, I'm using Google Cloud Storage, but you could use like the file system or any different pluggable system. So what I'm going to go ahead and do is I'm going to go ahead and upload a secret or put a secret. So I will say my secret is DevOpsDays, and my value is awesome. So what this will do is this will upload a secret. It'll get written. Again, it's encrypted in transit with TLS and encrypted at rest with AES GCM 256. I can get that secret back out. So I can get that secret back out. And I know this is exciting. It worked. How many people feel more secure? Yeah, it's OK. I'm always insecure. So I always like to pause here for a minute. And this is because the security industry, particularly like the enterprise security industry, has conditioned us to believe that security has to be hard. So there's this notion that if it's difficult, it's secure. So if I have to like run 50 commands and base64 decode something and then like put it on the back of a Tesla and drive it down the road to get the plain text value, it must be secure, right? And that's actually not the case. So Vault has been audited a number of times by many different independent auditing agencies, and it passes with flying colors. So what you see here is truly secure. But it doesn't feel that way, because as an industry, we've been conditioned to believe that security has to be hard. And it's my goal to convince the community that that's actually not the case. Security is quite easy, especially when you start thinking about codification and capturing these things as processes and APIs. This is a CRUD interface. So we're short on time, but you can create, read, update, delete, and list these secrets. I won't show you that, but again, encrypted Redis, encrypted memcached, very straightforward. This is great for things like Wi-Fi passwords or credentials that can't be generated on the fly. But as I said, Vault aims to be this kind of central store for secrets management. So one of these backends that we saw here is what we call the generic KV backend. There's another backend called the transit backend, which behaves very similarly. With the generic KV backend, we gave Vault data, it encrypted it, and stored it. With the transit backend, we're going to give Vault data. Vault is going to encrypt it and give it back to us. So there's a slight difference there. Instead of Vault storing it, it's going to return it as a response, and it's our responsibility as the caller to store that somewhere. And this is very common when interacting with like databases. So if you imagine you have a database with 100 million customer records, and you need to encrypt something like social security numbers or credit card numbers or passport numbers, right? You ideally want, you don't want to store that data in Vault. That's a lot of data that puts a lot of overhead on Vault. Instead, you give Vault the plain text data, and Vault gives you back the ciphertext which you store. And then when you want the plain text, maybe you need to do the credit check or whatever, you give Vault the ciphertext, and assuming you're authorized and authenticated, Vault gives you back the plain text. It's just encryption as a service. So this is actually very similar to like a cloud KMS service. So let me show you what transit looks like. So I'm going to go ahead and enable the transit secrets engine, if I can type. So you know this is a live demo because I keep messing up. So I've enabled the transit backend, the transit secrets engine. And now what I'm going to do is I'm going to create an encryption key. Transit keys my app. So I've created an encryption key. It's actually a key ring. I can go into more detail if you're curious. But this is an encryption key. So my app here, this little part, is kind of like a symlink or a pointer to an encryption key. And Vault does not divulge that encryption key by default. I'd have to explicitly enable it to divulge that. So I don't know what the encryption key is. What I can do is I can say, hey, Vault, can you encrypt some data for me? So I ask Vault to encrypt using the my app key, whatever that is, whatever that encryption key is, I don't know. Use the my app key and encrypt this plain text, plaintext. And the plain text has to be base64 encoded. The reason for that is that there's no requirement that the thing you're encrypting is representable as text, right? It could be like a Word document or a PDF. So we'll have to base64 encode that data. That's OK. I get to teach people the 3 less than sign trick, which a lot of people don't know about. It's super cool. It's basically the same as a pipe. I typed base wrong, but that's OK. So what I did here is I base64 encoded hi, and then I passed that, and I got back this ciphertext. So I would take this ciphertext here, including the whole thing, the Vault v1 at the beginning, and I would put that in my database in some row attached to a customer record. And when I wanted that value back, I would extract that value from the database. I would take this, and instead of running transit encrypt, I would run, who can guess it? Decrypt. I know, it's crazy. Same kind of symlink or name of my app. And instead of giving plain text, I'm going to give the ciphertext. And I don't have to base64 encode that because it's already safe. So I'll just paste it in there. And I get back agakaka, which is not hi. And the reason for that, again, is that the data is base64 encoded. So if I were to, echo this person to base64 to code, we get hi back, right? So this is incredibly scalable. So instead of having every Ruby and Python and Node.js developer write their own encryption in their own language, we now have encryption as an API. You post some data, you get the encryption back. And your security team and your vulnerability and your privacy team, right, they're controlling the algorithms and stuff that happen under the hood. Vault is incredibly configurable. You can pick from a number of algorithms here that'll do that encryption. So we saw two backends. We saw where Vault stores the encrypted data, and we saw where Vault encrypts it and gives it back to you. Honestly, most of you in this room could build this in an afternoon. Where Vault really gets powerful is its ability to dynamically generate secrets and revoke them at any time. So what I'm going to do here is I'm going to start a Postgres server. Oh, man. I didn't have Docker running because I have a battery on my laptop. We have to wait for Docker to start, so I might need like another hour. Sorry. OK, cool. Come on, you can start. I know it. It's almost there. I think we might be good. No. OK, we're good. So we've started Postgres. This is like the worst live demo you've all seen, right? I just started Postgres in the background, just using localhost here. And now what I'm going to do is I'm going to show you one of the scripts that I've been running, which is configure database. So this is just a bash script. There's two important lines here, two API calls to Vault. First, I'm enabling the configuration to connect to Postgres. So basically, I give Vault kind of the root credentials or very privileged credentials. And on the next block of code here, I give Vault the SQL to run to create a new user. So that's what you see here. And again, if you're not an expert in SQL, all you need to know is that this is kind of a Postgres command that grants read-only on everything in the current database. So what this is going to do is it's going to create a role. And anytime I read from that role, Vault is going to connect to Postgres. It's going to run this SQL, but it's going to fill in the username, the password, and this expiration, which we'll talk about in a second, dynamically, each time I read from that. So let me go ahead and run this. So first I need to enable the database secrets engine. And then I will run the configure database. Oh, no. What did I do? Help. I broke it. But actually, what did I do? I can't connect to Postgres. It's totally there. Live debugging, it's a real thing. OK, it's fine. We'll skip this section and move on to the next one. So what Vault will do, this was like the most exciting section. How much time do I have?
You have 8 minutes, and then it's break after. So.
OK. Why are you being sad? OK, we're just going to cheat real quick. We're going to jump over here. This is how you know I'm a real engineer. Did I run this already? Yeah. Ha! Fixed it. Actually, this is a screen recording. I'm kidding. No. That's be really impressive, right? OK, so as I was saying before I was so rudely interrupted by technology, so I've configured this database, and I have Vault talking to this local Postgres service. And what's going to happen is when I ask Vault to generate a credential, it's going to fill in that username and password dynamically. So it's probably best to just show you that. So what I'm going to do is I'm going to go ahead and read from database creds read-only. What this is read-only, just like my app in the previous one, is like a symlink to this role or this set of SQL to execute. So what's going to happen is Vault connected to Postgres, in this case on localhost in a Docker container, and it actually generated a username and a password. That's a real Postgres username and password that has access to read everything in the schema. And the reason for that is that if we go back up here, we can see that the SQL is granting select or read on all tables in the schema. And I can actually authenticate using these usernames and passwords to Vault. One thing that you'll note is that each time I run this command, and under the hood, this is just an API call. So everything that I do here on the screen is available via the API. In fact, there's nothing you can do via the CLI that isn't available via the API. The CLI is just a very thin wrapper around curl, basically. Notice that the username and the password are different. Right? The usernames both start with vtoken read-only, but the values after that are different, and the passwords are different. Each time I read from this endpoint, I'm going to get a new database credential. So let's take it back to the beginning, where we said applications and services authenticate to Vault and request credentials. That means that when your service boots, it gives maybe a certificate or some instance metadata to Vault. Vault validates that and says, OK, here you go. You can talk to me now. The service then goes to Vault and says, hey, I need a Postgres password for the foobar application. Vault dynamically generates a credential that is unique to that instance of your service or application. No other instance of that application or service has those same credentials. So that if those credentials are breached, you have what we call provenance. It's a one-to-one mapping between a credential and its entity that is using it. So you can revoke that credential and take down exactly one instance of your front-end application, for example. But what about kind of bigger break glass scenarios? So let me just prove to you that these things exist. So I'm going to run du, and you'll see that there are 3 users, because I ran that 3 times. So these are the 3 users we created, and then the Postgres user, which is by default kind of like the root user. Let me quit this. What if we have like a massive security breach, where we're like, oh crap, what happened? Or actually, let's, how do we fix that? Well, we can actually seal the vault. If we seal the vault, it'll stop our servicing requests, but that'll also block like transit and the key value store and any other secrets engines we have configured. But instead, what we can do is we can actually revoke all of these credentials that we dynamically generated. So everything on database, release, revoke. So what this does is Vault actually goes and revokes these credentials early. So if I connect to Postgres again, and I run du, all of those users are gone. So you can imagine this is like a terrible scenario. You're getting hacked. Your data is being hemorrhaged. How do you stop the hemorrhaging, right? Kind of what we call the break glass scenario, right? In case of emergency, break glass. One thing that's interesting that I forgot to point out is that if I run this again, connect to Postgres, du, notice that there's this password valid until some date in the future. And also notice that whenever we generate one of these users, it has this least duration of 1H, or 1 hour. What that means is that after 1 hour, or 60 minutes, or 2 30 minutes, or 4 15 minutes, after 1 hour, Vault will revoke that credential. So it's up to applications and services, kind of similar to like a DHCP lease on an IP address. They have to continuously check in with Vault and say, hey, I'm still using this credential. It's still being used. It's still being used. And this prevents secret sprawl, right? Because we're dynamically generating these credentials, but we can have them very short-lived. So if they only live for, say, 5 minutes or 10 minutes, we have a very small surface area for an attack. But the application can request an extension the same way that your laptop or your computer can request an extension on its DHCP lease. OK, so that's databases, supports Postgres, and all that other stuff. The last thing I want to show you is TOTP. Who knows what TOTP is? Cool. TOTP is like the academic name for multi-factor authentication. It's that thing with like the 6 or 8-digit codes. You get a push notification, SMS, et cetera. How many people have ever written TOTP or read the TOTP white papers? Yeah, it's really not fun. Like, is it fun? No, it's not. He shook his head no. It's not fun. So I've done it, right? I've done it in Ruby and Node. So what Vault does is it actually has this ability to act as a TOTP generation system. So if you want to offer two-factor authentication, say for your web application, instead of building that in the language that you're using for your framework, you can delegate that to Vault entirely. So I can go ahead and, oh no, I have to type this by hand. Generate. I do have a cheat sheet here if y'all haven't figured that out. OK, so here I ran this command. I said, hey, generate a TOTP key for Seth. That's a symlink name there. And it gave me back this blob of things. This blob of things is actually a base64 encoded QR code. I'm hurrying. So this is a QR code. I promise this is going to work before time is out. OK. So I'm going to go in here. I'm just using 1Password, but you could use any TOTP thing. I'm going to, because I can show you, I'm going to do this really cool thing, which is always fun. So you come up here, and you're like, boom, scanned, save. And that's a real TOTP code that I could go back to Vault, and I can say TOTP code Seth code equals that, and it's true. That's all I have for you today. Thank you very much.